Hey everyone, welcome to week 3 where we're going to do the chapter 7.5, which is basically just compound interest. So we're just going to backpedal really quickly. And our goal today is to compare the effect on investments of changing interest rates. Okay, so we're going to have a look at some graphs today, and we're also going to be rearranging our compound interest formula as well to find like principal values, interest values, and actual N for compounding periods as well. So let's get into it. So a graph of an investment for different compound interest rates can assist in comparing the effect of changing interest rates. For compound interest graphs, the interest rate affects the slope of the curve. So let's highlight that sentence because that's a really important one. An increase in interest rates increases the value of the investment, which causes the curve to move away from the horizontal axes more quickly. This is an example of exponential growth. So exponential growth we talked about last term as well when we were talking about our geometric sequences. So let's have a look at an example of that. So if you just want to write some theory, you can just write what is highlighted in blue as long as you have this example graph on there as well. So question 8 wants us to compare. It says describe the effect of increasing the compound interest rate. Describe the effect the compound interest rate has on the investment. So there are two things that we would be looking for in a graph like this. Okay, so you notice first of all, if we have 4%, 6%, 8%, 10%, the higher the interest rate, the larger the return on the investment. We can see that at all points. The orange line is always above the green line, always above the pink line, always above the blue line, and so on. But the other thing to note, and I'll write all this down in a second, and the other thing to note is that it is in fact increasing more quickly. Because as time goes on, look at how these gaps between the investments are getting bigger and bigger. All right, that's our exponential growth idea. So in other words, we've got an increase in interest rate increases the future value. Yep, makes sense. And according to this graph, there's a steeper curve for highest interest rates, and the steeper curve tells us that investments increase faster. So I'm going to write that down now. And if you would like to, you can fast forward through this part while I'm writing because I write very slowly. So we want to say an increase in interest rate increases the future value of the investment. Okay, makes sense. We probably didn't need a graph to tell us that. The other thing we want to do is we want to refer to our graph and we want to say the graph shows a steeper curve for higher interest rates meaning investments increase faster. There we go. So I've got two key points of information there. We've got increasing the future value of the investment and that there's a steeper curve, meaning that investments increase faster. So they don't only increase, they increase at a faster rate. All right, let's have a look at the next example. Using the compound interest formula here, we're going to have a look at example 9. Calculate the interest rate per annum required that would enable an investment of $4,000 to grow to $4,200 over 3 years if the interest is compounded every 6 months. Okay, so this is just a little bit different to 7.4 in that now we're looking for I rather than looking for A. Let's get to it. So, we know that A is equal to P1 plus I to the power of N. Okay, so let's substitute in what we know and what we've been working with our understanding of compound interest. So our final amount will be 4,200. Our principal is 4,000. 1 plus, now we don't know I. We're going to leave it there. That's actually what we're trying to find out. But we know whatever it is will be divided by 2 because we're compounding every 6 months or twice a year. To the power of n. Now, 3 years every 6 months means we're going to have 6 compounds or 3 times 2 compounds. So the first thing I'm going to do here is rearrange my equation by dividing both sides by 4,000. Okay, so that gets rid of the 4,000 on that side. And I end up with, on my left-hand side, 1.05 is equal to 1 plus I on 2 to the power of 6. Now we're going to do something kind of weird. We're going to take the 6th root on each side. Now you're going to have to locate this button on your calculator. I know everyone's calculator is a little bit different. It should have a little X there or something. So you want to put a 6 there. Okay? So that's sort of what the button looks like. And I think that in your calculators it'll actually come up and you can put a number here and a number here as well. So we're going to take the 6th root of 1.05. All right, and that 6th root cancels out that power of 6 on that side there. So we end up on the left-hand side with 1.00816. Now I have rounded that number, is equal to 1 plus I on 2. Now I'm just going to keep rearranging. Minus 1 from both sides. 0.00816 is equal to I on 2. Multiply both sides by 2, which means that 0.0163 is equal to I. So if I move over here now, if I is equal to 0.0163, that's not a percentage yet. Let's multiply that by 100 to get it as a percentage. That's 1.63% per annum. And that's our answer. That's our interest rate if we want to get from $4,000 to $4,200 over 3 years, compounding every 6 months. The next example we have here is we're actually calculating the length of time required for $3,000 to grow to $4,000 at 5% per annum compounded quarterly. So this is a little bit different. We're now going to be looking for n. So we know A, P, and I, looking for n. So we have our famous trial and error coming back to haunt us here. But let's get cracking. A is equal to P, 1 plus I to the n. So that's just our general formula. It's always nice to state that. So we have 4,000 equals 3,000 to the power of 1 plus. Now, we're compounding quarterly, so 0.05 over 4 times per year to the power of n, or rather to the power of n times 4. Okay, so we're just going to, for now, just simplify all of this, all right? So I'm going to divide everything by 3,000, okay? So I end up with 1.3333 equals 1.0125 to the power of n. And guys, this is where we're going to use trial and error. Okay, so basically you're going to put in different values of n now. You're going to go 1.0125 to the power of n as many times as you need to get the answer 1.33. And if we keep doing trial and error, we end up with, like for example, I did 1.0125 to the power of, I think 25, and I got the answer 1.3642, so that was too big. I then did 1.0125 to the power of 24, and I got 1.3474, too big. And then I did 1.0125 to the power of 23, and I got 1.3307, too small. Okay, so remember, if we want our investment to be $4,000, we can't come short. So our answer in this case is here. So therefore, n equals 24 compounding periods. And now the thing is, because we have 4 compounding periods a year, because we're compounding quarterly, we can just divide that by 4 and realize that that's 6 years. So in other words, it will take 6 years for $3,000 to become $4,000. Okay? Now, once we've had a go at those, so as you can see, it's very similar to 7.4, but we're looking for different values here. Here we were looking for I, here we're looking for N. So have a go now at exercise 7.5, questions 1 to 13. With question 2 and question 11, it asks you to use technology or use Excel. We don't want you to use that. Just use your calculator and the iterative method to help you here. Okay?